who's ever recovered from a period of cardiac arrest due to a heart attack or other cause will have suffered a period of brain silence and still woke up as themselves. Barbiturate comas can turn off brain electrical activity for periods of days and still permit later recovery. And the same effect of turning off the brain electrically will happen at hypothermia less than 18 degrees Celsius. One of the earliest studies on brain freezing was performed by Isamu Suda in Japan way back in 1966, and he in fact published this work in Nature, and he found that cat brains could recover normal electrical activity after 5 days frozen at minus 20 degrees Celsius. And in a follow-up paper, he showed he could even get partial return of electrical activity after these brains were frozen for 7 years at minus 20 degrees C, partial return after weeks at minus 60, but no return of integrated electrical functioning after cooling to minus 90 degrees C. And we can understand that by the fact that he used just 15% glycerol, because we've got this effect to consider again, that the amount of volume that's left unfrozen as you go to low temperature depends on the concentration of cryoprotectant, and with only 15% glycerol, you're probably going to look more like this at liquid nitrogen temperature than like that. So this is an actual light micrograph, by the way, of a brain that was cooled to liquid nitrogen temperature with only 15% glycerol in it, and you can see that this tissue looks more like frost on a window pane than brain tissue. And that's what happens when you straight freeze brain tissue without proper cryoprotection down at very low temperatures. So it's a given that to successfully cryopreserve a brain, you have to use more cryoprotectant than just the 15% Suda used. If you go to 40% glycerol, you get results on electron micrographs that look more like this. There's still holes where ice formed, but there's much more recognizable structure. So this then raises the question, well, what happens if we raise the glycerol concentration further? Because, by the way, this was the technology used in cryonics for those who are interested back in the 1980s. And then in the 1990s, cryonics organizations went to, or at least Alcor anyway, went to 60% glycerol. And that actually led to a landmark study by Mike Darwin and collaborators that was published, privately published back in 1995, showing remarkably good preservation using 60% glycerol in canine brains. And here you see an electron micrograph from that study. These holes here are not ice holes. These are actually capillaries, small blood vessels in the brain. And this is gray matter of the brain. And these circular objects here are cross-sections through axons that pass through that gray matter. And there's no sign of ice damage in this slide. Here's a close-up of an actual synapse. And what's amazing here is if you look at the synapse, you can actually see vesicles in it, these tiny pockets of neurotransmitter preserved intact by this freezing process. Here's white matter from that study. These circular areas, again, are myelin wrapping axons that pass transversely through the slice. No sign of ice damage, just a dehydration artifact. And every now and then, every 20 to 30 microns or so, you do see stuff like this. So there still is ice forming in the brain, which means we really want to increase the cryoprotectant concentration even further to see if we can get rid of ice completely. In other words, what happens if you actually vitrify a brain? And that question was answered in a study that Alcor published last year, actually, in Annals of the New York Academy of Sciences. This is brain tissue that was actually vitrified. And what you see is no ice damage. You just see these streaked white areas, which are caused by dehydration induced by the cryoprotectant. Here's another slide showing very dense neuropil with no ice damage. This tear here is actually a slice preparation artifact. It's not a result of the cryopreservation process. And also I'll mention that that study I just showed you on brain vitrification was performed using M22 cryoprotectant, which is the same agent that my company used to successfully recover rabbit kidneys from a state of vitrification. So this is a solution that is under laboratory conditions capable of vitrifying in very large volumes, even a volume equal in size to a human brain, So we can extrapolate from that. It appears that even the human brain can be vitrified with current technology. Now, I have to emphasize, this means structural vitrification. I'm not talking about viability or preservation of metabolic function, but as we look at brain tissue under electron micrographs, it looks like current technology is adequate to preserve the structure of the tissue, even in volumes as large as the human brain. The outstanding issues are cryoprotectant toxicity, which is still not well understood and needs a lot more work. Fracturing. If you store either vitrified or frozen material way down at liquid nitrogen temperature, you almost inevitably get fractures forming in the tissue due to thermal stresses as you go far below the glass transition temperature. So the moral of the story is don't store too cold. And of course, since we're talking about suspended animation of whole people, we're only talking about the brain. What about the rest of the body? That's a pretty big question mark. There's two perspectives you can use to look at these outstanding issues. Since this is a life extension conference, it behooves me to mention the cryonics perspective, which says it's still worth doing cryopreservation today because in theory cryoprotectant toxicity, whatever its details are, could be reversed by future chemical repair technologies. Fracturing could be healed with nanotechnology theoretically, and the rest of the body could be regenerated theoretically. This means that the overarching question for cryonics is, does vitrification erase the essential information content of the brain? And I think that it's pretty unlikely that it does, but until there is truly reversible brain cryopreservation, we can't really prove that definitively. It's a probability estimate based on the data we have. The perspective that my company uses is what I would call the cryobiology perspective, which means we deal with cryoprotectant toxicity by developing less toxic solutions. We deal with fracturing by storing at higher storage temperatures. And if we want to talk about cryopreserving the rest of the body successfully, we need to do much more research. So from the orthodox cryobiology perspective, the overarching question is vitrification demonstrably reversible, which currently it isn't for large organs or people. I'll just conclude by saying where we are now and where the future is going with these things. At my company, we've been able to successfully vitrify corneas, cartilage, small animal organs. Optimistically, we may be able to scale up to large human vital organs within a decade. Reversible cryopreservation of the brain, if there's enough interest to support that research, it may also be doable within a decade because the brain is, after all, just another large vital organ, and it has some favorable cryobiological properties like a very high blood flow rate, which permits quick equilibration with cryoprotectant, technically speaking. And then there's this question of, well, when will we have demonstrably reversible whole body preservation? And I think that that's probably still off somewhere in the middle of this century. I'll just conclude by thanking those entities that support our research. That would be the Life Extension Foundation and the U.S. National Institutes of Health. And I thank my colleagues, especially Dr. Gregory Fay, who is the mastermind of most of these breakthroughs in vitrification over the last 20 years. Thank you very much.